For this problem, a proton is accelerated from rest through a potential difference of 50,000 volts. So what happens in this part is we have a proton right here. It has a charge of plus E. Charge of the proton is 1.6 times 10 to the minus 19 coulombs. It's accelerated through a potential difference, so it starts at a positive plate, feels a force which pushes it to the right towards the negative plate. The negative plate is at the lower potential. We say that's at 0 volts. Our positive plate is at the higher potential, 50,000 volts. It has an initial velocity of 0 because it starts at rest, starts to move to the right until it gets to this point where it's moving with some velocity v final. We want to find out what is that v final. So for this part of the problem, let's apply conservation of energy. E final equals E initial. So K final plus U final equals K initial plus U initial. K final is a half times m times V final squared, plus U final is the charge on the proton times the final potential, equals K initial, a half times m times V initial squared, plus U initial, which is the charge on the proton times the initial potential. So now let's see what's 0. Our final potential is 0, so our final potential energy is 0. Our initial speed is 0, starts from rest, so our initial kinetic energy is 0. So a half times m times Vf squared equals Q times V initial. Solve for the final speed. So we have the charge times the potential divided by a half times the mass. Then we have to take the square root of both sides. Charge on the proton is the fundamental charge E. Mass of a proton is 1.67 times 10 to the minus 27 kilograms. Put all this in through our calculator and we get 3.10 times 10 to the 6 meters per second. That's the speed at which the proton enters through that little slit and goes into the magnetic field. Once it's in the magnetic field, it goes through a circular path and strikes 1 millimeter below where it started. So it goes around something like this. So this distance is 1 millimeter, so the radius of that circular path would be a half of a millimeter, so a half the diameter. We want to find the magnetic field. So magnetic field is a vector. It's going to have two parts, which is going to be the magnitude and the direction. Let's deal with the direction first. As the proton goes into the field, the velocity points this way. The direction of the force must be down because it swings it downwards in a circular path. So there's our magnetic force. Let's think about our right-hand rule. With our right-hand rule, the speed is our thumb. Our index finger is our magnetic field, and our magnetic force is our middle finger. So let's apply our right-hand rule. It's a little bit hard to twist my wrist, so I'm just going to move this sheet of paper, change the orientation a little bit. That'll help. So V is my thumb, FB is my magnetic force. Oh, I'm still having trouble. I'm going to twist the paper a little bit more. So V is my thumb, points this way. FB is my magnetic force, points down that way towards the bottom of the sheet of paper. And the magnetic field is my index finger, which is pointing straight up out of the page. So by the right-hand rule, magnetic field is out of page. Now let's go ahead and find the magnitude of that magnetic field. What we know about that proton in the field is that the sum of the forces that act on it are mass times acceleration. The only force that acts on it is the magnetic force. That has a magnitude of Q times V times B. It's going in a circle, so instead of A, we can say V squared over R. So one of our V's cancels. We can bring our Q to the other side. And remember, Q is the charge on the proton, which is the fundamental charge E. R is the radius of our path, which we said was 0.5 millimeters, so our magnetic field turns out to be 64.6 Teslas. And because it's a vector, we have to give the direction, so we'll say out of the page. We could say plus K hat if we put on our Cartesian coordinate system. So there's our magnetic field in that problem.